All right, the back of your spirals, if you don't know what to do, you are graphing. First of all, good practice on graphing. What, those of you that have gotten this graph, what have you gotten? What does he look like? Oh, that's good. Where is the V? Where is he? 1/2 to the left. If you couldn't tell, maybe you should have zoomed in a little bit. Remember the negative 10 to 10, that's a lot of units if it's only moved negative 1/2. Can anybody tell how we could have figured out that this was a V shifted 1/2 to the left? How could this means V, right?
Yeah.
So that would have told us a V, but how could we have gotten 1/2 to the left?
It's inside.
It's inside. We could have maybe set 2x plus 1 equal to 0 and find the intercepts, right? The y-intercept, assuming that it hit there. And that would have gotten us x is equal to negative 1/2. That's one way. What's another way, though? Didn't we talk about shifts? Didn't we talk about addition going on the inside is going to be a shift? What do you do when there's a 2? Is this really on the inside? It's on the inside of the absolute value. Rather, is it on the inside of the argument? No, but how do we make it on the inside? Pull out a 2. We're pulling out a 2 from 2x. What do we have left? X. But pulling away a 2 from 1, what does factoring really mean? Are we subtracting? Are we multiplying? Dividing. So what's 1 divided by 2? Do you see the shift left 1/2 now? Dun, dun, dun. Now what technically else has happened? Don't I have some sort of stretch? Wait, is that on the outside or is that on the inside? It kind of looks on the outside. We can actually put it on the outside because what's the absolute value of 2? So we could actually move this in and we're not doing anything wrong. We're actually just fine. You can put in parentheses or you can not put parentheses. Absolute value of 2, well, we don't really need them in the absolute value, so we could just pull them out. We could say a vertical stretch by 2. What's going to happen to my V if it gets vertically stretched? Up and narrower, right? Or, didn't we say a horizontal compression by 1/2? What's going to happen if I horizontally compress by 1/2? Up and narrower. Oh, it's the same thing. Go figure. Long story short, do we have a graph? Yes. Why is it not 1-to-1 right away? Because it fails. Well, it passes the vertical line test, but what does it fail? The horizontal line test. So they're telling us in letter A, and then I think you had one homework problem like this, maybe 2. Restrict the domain. So cut down the x values to only include a part that passes the horizontal line test. Well, do you think we'd rather have x's from or towards negative infinity or x's towards positive infinity? What seems more natural to keep? Okay, so we're going to keep x's towards positive infinity. We're going to keep this side. But as we come down this side, question, when is he going to start failing the horizontal line test? Right where? Right here. So we're going to say, you know what, sorry buddy, this doesn't work for us because this makes you fail the invertible test, right? Fail the horizontal line test, and you make the inverse not be a function. So how do we disregard that? We ask ourselves, what x's are we going to use? Where's that point at? Negative 1/2, 0, right? So I'm going to say, all right, we have to restrict the domain. We have to tell the domain, you have to be greater than 1/2 to infinity. Or another way of saying it, x, you're allowed to be greater than or equal to 1/2, but you can't be below. Sorry. If we go any further to the left, you're going to fail the horizontal line test. You're not going to be 1-to-1. And that's not going to work for us. Does that kind of make sense? If we had a parabola, like maybe a homework problem, if we had a parabola, where could you cut it? Where could you restrict it? Where could you stop it? Stop it at the vertex. Wherever that vertex is, be like, oh, sorry, everybody on that side, you don't work. But everyone greater than or equal to, all the x's greater than or equal to, you do work. Now, how do we find f inverse of x now? Some of you are stuck because you're like, they're absolute value bars. That stinks. Okay, I get it. It does stink. I understand. But what did we just do? Didn't we just take away part of the absolute value? And what do we have left? A line. A which line? Absolute value. Remember, a positive comes out and a negative comes out if we're trying to solve? Did we keep the positive or the negative? We kept the positive. So which one do we keep? Oh, find his inverse. He's the only part we have left anyway. Does that make sense? We kept only the 2x plus 1 part. We didn't keep the negative that was flipped. So all we have to do is take the inverse of him. So remind me from last night. He's not one of those crazy hard ones like the SAT math problem. How do we get an inverse? Not yet. No minusing 1 until we switch the x with the y. Good. We switch the x with the y, so we get x is equal to 2y plus 1. Then we subtract the 1. I totally agree. And after we subtract the 1, what are we going to do? Yeah, divide by 2. So we'll get y is equal to x minus 1 over 2. That's one way of writing it. If some of you guys wrote it another way, 1/2 times x minus 1, you're still right. If you decide to distribute him in, you're still right. All those are good. But I'm not good until I do what? To finish off finding the inverse. Yeah, I need to change that y, because y is f of x, and I need to say, no, he's my inverse, right? Let me just steal that first one that we found. Okay. There we go. So we have our restricted domain, whether you wrote them in intervals or inequalities, both of them are right. We have our f inverse. What's the last one? Oh, state the domains and ranges of both. Well, which one do we already have a picture for to hopefully make it easier to state the domain and range of him? The f of x, the original one. So hold on, look at that original one. I think you guys hopefully already know this answer. For f of x, who's his domain? What we said, yeah, in letter A. X greater than or equal to, we'll write it the easy way. X greater than or equal to 1/2. How left does it go? Remember, we had to cut it, so it's only going to go left to 1/2. Oh, wait a minute. What am I not putting? The negative. What am I thinking? I don't know. Did you guys say something I just didn't hear you, or did you just leave me floundering and not help?
I thought you were smarter than me, so I raised my hand.
Oh, man. Even people smarter than you every now and then need perhaps
She is smarter.
a little help. I said even. Life lesson. Maybe in some things, probably not in others, though, to be honest. Let's come back. How low does it go? Only to 0, right? How high does it go? Positive infinity. So if we were to do intervals, we would say from 0 to infinity. If we were to do inequalities, we would just say y greater than or equal to. Huh. Well, that's the original. Man, this is rough. How on earth are we going to do the inverse? This is forever.
Just reverse it. Switch it.
Switch it. Right? If x's and y's switch, what else switches? Domains and ranges. So we can go ahead and say, sweet, we already have one. No big deal. For f inverse, switch it. Meaning, keep the d, keep the r, keep the x, keep the y. But instead of being greater than or equal to negative 1/2 for domain, that's going to now be in the range. And instead of greater than or equal to 0 being with the y's, with the range, now it's going to be in the domain. Is that easy as a quick switch? I don't know about apple pie. Although apple pie is hard. Making your own crust. Just saying. Like pinching the sides and then we'll
Apple pie with store-bought crust.
stop. Homework, let's go. Homework, let's go. We have some checking to do. Technically, actually, peeking your spirals, you should be able to tell by the presence or absence of red marks. Did we ever check 1.8?
No.
Oh. Let's start in 1.9. There's not a lot of evens. There aren't a lot of evens, I don't think. And then we'll go ahead and go back to 1.8. Thank you for that resounding no, so we can quickly proceed. Alright, red pens out the front of your spirals. Homework number 9. Let's start here. Homework number 9. Let's start here. You guys can see number 2, the notation. Am I saying this right? F to the negative 1 power? No. Fail. What should I be saying? F inverse. Number 4. Hey, I think that one was talking about symmetry, yeah? Symmetry across inverse functions across the y equals x line. Number 14. I think you were verified, right?
Yeah.
And how do I know that? Because I told you to verify, plug into that description of, if you plug one into the other, everything should go away but x. And if you go vice versa, everything should go away but x. Does it work?
Yeah.
You did it properly. Yes, indeed it does. Yes, indeed it does. Number 20. Who is he the reflection of?
X2.
Is that what you were doing? Were you flipping him across the y equals x? He'd be the reflection of this one, right? That could be a little hard. Unless you did your little, kind of. You did your little y equals x, and you remember you take one piece at a time. My ones who were a little stuck on that one. If you're trying to reflect him, draw your y equals x line and take one piece at a time. Because that's how I do it. Or you could have seen that he was x cubed. You could have found the inverse to be the cubed root of x and then graphed it. I guess that could have worked. Number next one. 26. They gave you 2 functions. They asked you to verify them. Gave you 2 functions, asked you to verify them. Was anybody confused about how to do 1 over 1 over x? Right? Or you saw this and you're like, yeah, that can't be right. Right? But was it right? The way that I deal with this, there are a couple different ways. Can I just show you my trick for complex fractions? And we'll use it more this year. 2 ways of thinking about it. One way is to write it like they did, which is write the big fraction bar as a division and then multiply by the reciprocal. That definitely works. To make the big fraction bar as a division and then change it to being multiplying by the reciprocal. That works. Another way is just to think about 1 over anybody. 1 over, isn't that just the reciprocal? 2, 1 over 2 is 1/2. Oh, that's the reciprocal. So what's 1 over x? The reciprocal x. That's another way. So here's a third way. A third way is to say, who's that hidden denominator that's messing everything up? Right? We're used to fractions. We don't like them, but we're used to them. There's a top, there's a bottom, there's another bottom. If you figure out who's making the problem, and if you multiply top and bottom by him, what ends up happening? Doesn't this just cancel? Oh, I just got rid of him. And where did I put him? Dun, 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 dun. Now you might be like, well, that's kind of dumb. Because this is easy in my mind, my head. But what if I was to give you something else? I'm recording, so let me try to do it up here. What if I was to give you something like 2 plus 1 over x all over 1 over 3? Come on, you guys all hate complex fractions, right? Could you do this whole get a common denominator, change the big fraction part to division, multiply by the reciprocal? That would take like 5 steps. Just kidding, maybe 4. Or you say, who are my problem people? 3 and x. If you multiply the top by 3x and the bottom by 3x, what happens? What happens to the 3 in the bottom? Oh, it's gone. You end up with over, who's left down here? Just x. What happens when you distribute the 3x by the 2? What happens when you distribute the 3x to the 1 over x? X cancels, wait, remember this is like over 1. The x cancels, and all you have is a 1 times 3. Look, 1 step and I'm done. Something to keep in mind. I'll keep showing you this year, but that's how I like to do complex fractions. They're not as hard as you might think. Question. They both worked out. They both ended up being x if you properly were able to do the 1 over x thing. But looking at the graph, why does it make sense that they're inverses of each other? Where's the y plus x line? What does it already have? It's its own inverse because it already has the symmetry across y equals x. Anyway, that was a weird problem. I think it was more weird just to start it than to actually work through and say, oh yeah, it works. Huh, go figure. Number 42. Weren't you just looking and graphing? And did you actually, how many of you didn't even actually need to graph it? And you're like, it's a squared, it fails. Nice. Those of you that did graph it, does it make sense it fails? That's not one of them. That's all they asked you to do. Number 52. All right, let me give you a second. Didn't you guys have to find the inverse on this one? Wait, what? What happened? Didn't it end up being the same thing again? It is its own inverse. I think there's a pattern to which ones are their own inverses, huh? Go figure. But does it work if you switch the x and y's and if you multiplied up and divided? Yeah, it works. Like that's how you solve for it, right? What happens with the graphs? They're the same. It's the same function, same graph. Why does it make sense? It already has that symmetry. We're good. Each function has both pieces already and it already has the symmetry. No big deal. Now, the last part might have been a little bit hard, domains and ranges. But remember, first of all, they're the same thing. So that kind of helps. You don't have to worry about switching anything. And second of all, domain and range. Domain. How left does it go? Forever. How right does it? Negative infinity, right? How right does it go? Infinity. But what can it not hit? Right? X can't be 0. Quick way of saying that. We can just say that. Range. How high does it go? Infinity. How low does it go? Negative infinity. But what does it not hit? And that's why, another reason, switch it and it's the same. Just can't equal 0. Is 64 your last even? Are we close? Let me give you a second. This one you have to solve for, yeah? Switch the x and y, solve for y. What do you think was the most common thing that someone might have missed when they were solving? That one. Why do we need plus or minus? When we put in a square root, if you just see something, I'll come back. You just see something like, I don't know, x is equal to root 3. Is that a positive number or a negative number, and why? Be confident. What is it? Positive or negative? Positive. Why? What's the understood sign? Positive. The root is given to me, so I just say, oh, it's a positive. What if I had something else like, what is it? A negative. But if I go putting in a square root, it could have been a positive or a negative. I have to put both. If it's given to me, I can say, oh, it's a positive, oh, it's a negative, whatever, right? But if I am putting it in, if I am doing the square root myself to undo a squared, right? That's what undoes a squared. When I'm putting it in, I have to allow for both options, positive or negative. Because a positive number squared equals and a negative number squared equals. I have to allow for both. Why did they not write it as f inverse? Because it's not a function. Those two pieces put together make a relation. So that doesn't work. And another way of thinking about it, does the parabola pass the horizontal line test? He doesn't pass the horizontal line test, so this isn't going to be a function. And you can tell because there are two pieces. All right. That, you said, was our last even, right? Yes. Were there any quick questions on odds? You could check in, you could look at Calc chat, and you were still stuck. Caleb.
Was 73 the one that we did, like the one that we...
It's like the one that we did in the back of our slide. Yeah.
Okay.
Yeah. So then check that out and then see maybe and let me know if you still get stuck. Anything else? You guys checking your odds? Getting them all right? Doing them and then checking instead of checking and then doing? All right. Section 1-8. You can just leave the horse to water. Section 1-8. It's been a while, so let's review real quick. 1-8 was all about combinations of functions and compositions and decompositions. If you were decomposing, you were breaking stuff down. Let's go ahead and check quickly. Number 2, the answer should have been composition. Number 10, he was a little weird. You probably thought there was more to do than there really was. Can we put these two together? No. Why? Different denominators, and he doesn't even have a radical. We'll just ignore whatever's going on here. Letter B, same thing. Some of you probably thought you should put it together. No. You can't. They're stuck apart. Letter C, the only way to put them together is to put him over 1. And put the numerators together, denominators together. Then you're stuck. There's nothing else to do. If you started pulling out stuff, you were killing poor little puppies. Letter D, he's a mess. But if I divide, I multiply by the reciprocal. So the bottom ends up on top and the top ends up on bottom. The tricky part might have been the domain. If I remember right, I think that's kind of tricky. What is this? But the domain. Do you see any domain problems in this big old nasty thing? Yeah, I see 2. I see a denominator and I see a square root. Denominators. What has to be true? Oh, so x can equal 0. That's from the denominator. That's one problem. What's the other problem? Yeah, whatever's under the square root has to be greater than or equal to 0. Now, long story short, when you solve, and it might have been a while since you guys did these nasty inequalities, how do we keep going? Square root plus or minus. If we do a positive square root, the inequality stays the same, so we get x is greater than or equal to 2. If we do a negative square root, this is going to flip, and I'm going to have negative square root of 4, which ends up being x less than or equal to negative 2. It might have been a while. You're thinking of what is greater than or equal to negative 2 and less than or equal to 2. So you get these two pieces. I said it backwards, didn't I? Less than or equal to negative 2 and greater than or equal to 2. It's not a sandwiched inequality because it's going outside in our number lines. And if we have negative 2 and positive 2 as our boundaries, do we even have to worry about 0 anymore? No, that's why they didn't put them, because 0 is not even an option. So, domain problems. I think we covered it in section 1.4. Some of you need to go back and review that a little bit whenever domain comes up and remind yourself, where do the problems occur? All right, let's keep going. 18. Double check. There were so many places to make mistakes. You could have killed a seal and not distributed. You could have killed a puppy and not foiled. You could have killed something else and just not even done the plug-in and been totally lost. But remember the notation. It doesn't mean times, it means of. So I plug in to F, and I plug in to G, and I add them all together. So then we FOIL. Whenever we have just a plus in front of a parenthesis, a little 1 can distribute in and it stays the same. Then we combined our t terms together and we combined all of our numbers together. Final answer is, some of you might have tried to factor, but you didn't need to. There was no direction to say to keep simplify. Couple seconds, you guys have the answer written down? Okay, let's keep going. Number 32. You draw your attention. A is 20 minus 3x. A is 20 minus 3x. B is negative 3x. C is x by himself. C is x by himself. Get the answers down. Don't have time to get to work. 20 minus 3x, negative 3x, x. Number 42. They asked us to think about domains. Domain problem, denominator can't equal 0, so x can't be plus or minus 1. But this one, no radical, no denominator, all real numbers, no big deal. What does the little hollow O mean?
No, it's
Everyone ignore it. What's the little hollow O mean? Of. F of G of X. Plug it in, plug it in. Plug what in? Who G is. G is X plus 1. Plug it in. Simplify by foiling. Not allowed, not allowed, not allowed. Poor little puppy. And then simplify. How did they get not 0, not negative 2? Denominator can't be 0. If you factor that denominator, you would end up with x times x plus 2 is what cannot be 0. And that's there. So hence we got our 2 zeros that were not allowed. They say with words, everything except, you could also just say x cannot be 0 or negative 2. Letter B, plugging in the other way. Here's your final answer. Did you get it? X squared plus 2 over x squared minus 1. Same thing, bottom can't be 0, so x can't be plus or minus 1 for the domain. Number 44. You guys can see the answers. Letter A was just a number. You have to do some work to get that number. So A was just negative 1 and B was 0. Write down the answers. A was negative 1, B was 0. Number 52, that was a decomposing one, right? F of G. You didn't even have an of H. It was just F of G. Who is the innermost? Did you guys get 5x plus 2? That's what I thought. And who is the outer? Well, everything else. 4 over x squared. That's the decomposing. Remember we looked for the innermost and then we did the different colors. 5x plus 2 is the innermost. 4 over something squared, call that something else. And then, oh, hey, yeah. There you go. Any quick odds that you guys remember? Remember, you can be grading your odds the night before or the morning after you finish your homework and see which ones you get wrong. Any odds in particular? Okay. How easy is it to make mistakes on compositions?
easy.
Yeah, it's really easy. You gotta be careful. So if you did make mistakes, it's not a bad thing. You're catching it now and trying to figure out what went wrong. Please come let me help. Go over them, and if you want to go over them on your own, then come back and be like, I don't know how to do this. I want to help, okay? Let's try my best. Let's get out of here. Let's go back to notes. Yes. What changes did I make? Okay. All right, here we go. Section 110, final section of chapter 1. Does that sound about right? Pretty close?
Wow.
What does that mean? He's coming.
Word.
Every possible word problem that you've ever seen or solved? No. Very specific ones in a very specific format with very specific directions. So don't freak out entirely on me. I'm just saying I understand the struggle, okay? I understand the struggle. But we're going to talk about strategies for how to attack these types of word problems. They're very specific. They fit into a very specific category. Mathematical modeling is the general category. Variation is the particular type of problem that we're dealing with. And maybe you've heard the mathematical modeling thing before. Maybe you haven't. Mathematical modeling means take a situation and figure out a mathematical model an equation, basically, that describes or can solve for or can show how that situation is working. For instance, in calculus today, we're talking about free-falling objects, and how their position can be modeled. What? Physics? And there is a mathematical model for how that motion behaves. As long as it's a free-falling object, meaning there's no sort of motor on it. It's just literally falling because of gravity. And that model, you don't have to write this down, that model is position is equal to 1/2 constant acceleration times time squared plus initial velocity times time plus initial position. Don't worry, we're not doing this one. But this is a model that we can plug into if we know at what speed something was thrown, like a ball thrown straight up and then it's falling to the ground. Or a water balloon thrown straight up and falling to the ground. Or a diver diving off a diving board and then going straight into the water. Ignoring wind resistance, just thinking about gravity, this model can show us, after so many seconds, exactly where something is. Anyway, that's what I mean by model. Some sort of equation that models the situation that's going on. Now, we already talked about how there are 4 main ways of looking at math. And you're going to keep on seeing these 4 different ways. In homework, in section 110, you're going to see a table and at least one problem. That's numerically. Information given to you numerically. You're going to have quite a few that give you a situation or a relationship verbally. You're going to have to translate what does that verbal description mean. You might be given a graph, a couple graphs, and you might even be given an equation or two. But the point of this homework is to figure out this thing called variation and how to translate between verbally and algebraically. That's the main idea. But first, in homework, you are going to see just a few problems on the line of best fit. And if we hadn't done the graphing calculator handbook and those worksheets and that quiz, we would have to slow down. Everybody got your calculators. Let's learn how to put lists in. Let's learn how to scatter plot or stat plot those lists. Let's learn how to find a linear regression. Let's learn whether or not it fits the data well. But haven't we done all that already? Yes. But if you don't remember, when you get to these types of problems in homework, if you don't remember how to do them, where should you go? Graphing calculator handbook. Go to that regression. Go to the stat plot and remind yourself exactly what buttons to push and how to get there. Just a hint, you have to use the list, right? You have to use the list and you have to use the stat and the calc. But when you see something like, they could say it 2 different ways, line of best fit or least squares regression line, either of them are just pointing you to the regression feature that we've already used. And just a hint, you're only seeing linear ones in this one. So it's going to be that, is it linreg? Is that what it is? Something like that. Maybe it's linear regression. You're just using the linear one, okay? Some of your calculators are going to give you an R value. Maybe you noticed that when we did the graphing calculator handbook. That's actually a statistics thing to say how good of a fit the model is to the data that you have. It's going to find you the best line it can, but that's not always. That's not always a great line or a great model. So there is this extra thing. I think this section talks about an R value, but since we're not doing stats, we're not doing AP stats, we're not doing regular stats, we're just kind of introing stuff. We're not going to stress about the R value, the correlation coefficient. But long story short, for those of you that are seeing it in your calculator, if it's close to 1, like 0.97, 0.99, that's a great fit. It's fitting it really well, which means it can predict. If the study keeps on going, you can probably predict what's going to happen. Let's keep going. Pause. You don't have to write this. Okay, pause. If you were given this problem, let's just quickly recap. If you want to get out your calculator, just peek at it. Just quickly recap. If you were given this problem, what would you do if they want you to find a least squares regression line? They want you to find a linear regression of this data after stat plotting it. What would you do? Don't do stat plot yet, though. What do you have to do first? But that's good. Plug into your Don't you have to do list and edit, right? You have to do your list and edit. You have to plug in all this stuff. Wait a minute. Why am I telling you don't use 2003, 2004? Yeah, it's going to be like randomly in the 2000s. You have to do the whole Zoom stat. And it's weird. Just make it 3 and 4 and 5 and 6, right? How many years from 2000? Is that better? We remember that? Kind of? Put in all of your data carefully. After we have it in our lists, how do we go ahead and get it into our graph? Turn on the plots, either from the y equals, zooming, or going up and hitting enter and selecting. Or you can hit second y equals, right? And turn on your stat plots. What's that zoom? I said it a second ago that helps you get to the data and have a nice picture. Zooms. I would do zoom fit. It won't know to look in the list. Zoom stat looks in the list and tells you or gets you a proper window. Let's see, besides zoom stat, what else do we have? How do we find the linear regression again? That one button, that one feature in that one menu that we find by math. It's stat again, right? Stat calc. There we go. You can go to stat, then you have to go over to calc, and then you have to do your linreg. Okay, long story short, that's all the review on that. You guys know what to do. And if you don't, go back to your handbook. And you should be able to find something like, right? And be able to graph the line. It should fit well and have the equation. Let's keep going. Okay. The big point of today, variation, and there are 4 types. Variation, there are 4 types. I'm not going to have you guys write the words to the examples. In homework, you don't have to write the whole word problem. You do have to give me the important information, but for class and for time, the way it is, we're just going to go ahead and not write the problems, but write the answers. Let's start. Direct variation. You guys have seen it. You guys have seen it before. It might have just been a while. Whenever we have this wording in problems, there's always a quantity that somehow comes before, and it should match up with the y value, or what goes on the left. And then there's a quantity that will show up on the right. However, one's on the right is going to match up with the x value. But variation, we have this extra constant k. K is called the constant of variation, or the constant of proportionality. It's not the same for every problem. It changes. It's not the same for every problem. It changes based on the context. An example could be the area formula of a circle. Pi r squared. Area is directly proportional to the square of radius. But we have this extra constant pi that's very important. So I'm using this as a pattern. Directly proportional means quantity equals k times other quantity. We could look at this example and start assigning variables like simple interest, which we almost always call I. I equals PRT, that's something maybe you've learned in the past. I is directly proportional to the amount of the investment. That's I too? No, we usually call him P for principal. Maybe. But if we were just to make a model, taking the clue directly proportional, what could we say? Who's on the left? I is directly proportional K times P. That's it. That's how to make a model, right? Directly proportional. Now, it could get a little bit harder. If we were to see something like the one below, the distance S, okay, they give me a variable. The distance S, an object falls, varies directly, okay, it just means direct variation again, as the square of the duration t. Okay, well, what would that formula be? Who's on the left? S is, or does, vary directly, k times who? The square of t. Some of you got it. Some of you were a little bit off. Okay, so you have to be careful. The distance S varies directly equals k times t squared. The words will be in the notes if you guys want to reference them later. We're just getting to see if we can translate right now. Now that's what kind of variation again? Direct. Ooh, so how does inverse change? inverse variation. It's basically the same. You have something on the left, something on the right. Something on the left goes along with y again. Something on the right goes along with x's. But what do you notice? It's no longer k times. What is it now? Yeah. Oops. That's not the right one. It's now k divided by. It's now k divided by. So we have wording inversely proportional. Wording varies inversely. But then when we get to an example, demand stands for, well, D, I guess, for our product. Varies inversely, there's our wording, as the price of the product. The price goes up, demand goes down, generally. That's an economics thing, though. Let's stop. So how will we make an equation if we know varies inversely? What's on the left? Demand. Varies inversely, K over, who's our like our X, P for price, right? Now done direct. Direct is K times. We've done inverse. Inverse is K over. What about combined variations? There's not really a formula for this. It just means some problems might have direct and inverse variations all related. And then we have this longer example. So we have direct, K times X, inverse, K over X, combined, some mix of direct and inverse. And the best way for me to show you that is just to go through another example. Resistance, I don't know, R. Of a copper wire carrying an electrical current is, now guys, this wording is great for the actual problem, but for you writing down a problem, just say resistance is, you don't have to write all the rest. Make it short and sweet. Directly proportional, directly prop, to, oh, I need a variable for length, right? L maybe? And inversely proportional to cross-sectional area, A. Okay, what's on the left? R. Directly proportional to, okay, K times L, and inversely proportional to, use the K twice. K times L and K over A. You can kind of have your constant just stay in that one little spot, and it'll have a direct relationship with one and an inverse relationship with another. Now careful, there's one more. Remember there were 4. What if we were to have, last one, joint variation? Now as you guys are writing this real quick, what are you going to see in homework? You're going to see some words, some examples that you're going to make into equations. You're going to see some equations that you might have to state in words as far as what type of variation. But then the rest of homework is going to be like, use the model that you found to take information and plug in and solve. Kind of like we did with the worksheets on our calculator handbook. So last but not least, I know, but let's get this last one in. Kinetic energy varies jointly, direct variation with what? Mass and square of velocity. Who's on the left? E. Jointly means direct with who? That looks kind of like a popular formula that we've seen before. Section 110, due Monday. Do the best you can. We'll hash it out. Questions that you have. And then quest corrections also. Bye guys. Quest corrections. We'll turn it on Monday. I can't even understand.